No place on Earth builds like New York, and in 2025, the scale is more outrageous than ever. Beneath its streets and above its skyline, billions are being spent to reshape the Empire State with projects so massive they defy belief. In this video, we'll show you New York's megaprojects under construction in 2025, and why the city that never sleeps is now building like it never has before. The reconstruction of 270 Park Avenue in New York City stands as one of the most technically ambitious skyscraper replacement projects ever undertaken in an urban environment. Originally the site of the Union Carbide building, completed in 1961, the location underwent a full demolition starting in 2019 to make way for the new headquarters of JP Morgan Chase. This feat is particularly notable as it marked the tallest intentionally demolished building in the world at the time, standing at approximately 707 feet tall. The challenge of bringing down such a massive structure in the densely populated Midtown Manhattan district demanded extensive logistical planning and engineering precision. Deconstruction began with internal strip-outs and the abatement of hazardous materials like asbestos, a common element in mid-century construction. Crews worked from the top down, floor by floor, using controlled dismantling techniques rather than implosion due to the surrounding high-rises and the proximity to active transportation infrastructure such as Grand Central Terminal. Temporary structural reinforcements were installed to maintain safety as each floor was carefully disassembled. Scaffolding and protective netting enclosed the structure, while vibration monitoring and dust suppression systems were deployed to limit the impact on neighboring buildings and pedestrians. Following the complete removal of the original structure, foundation excavation commenced for the new tower. Deep caissons were drilled into the Manhattan schist bedrock, a process requiring precision, boring rigs, and careful sequencing to avoid interference with existing subterranean utilities and tunnels. Once the foundation pilings were in place, a concrete mat slab was poured to distribute the load of the superstructure, utilizing high-strength concrete mixes with additives to reduce shrinkage and accelerate curing times. The structural system of the new 270 Park Avenue, designed to exceed 1,200 feet in height, relies on a hybrid steel and concrete core with a perimeter bracing system to enhance lateral stability. Erection of the steel superstructure was carried out using tower cranes and advanced sequencing to allow for concurrent installation of mechanical systems and curtain wall panels. Floor plates were constructed using composite steel decking with poured concrete slabs, designed to maximize open-plan office flexibility. Mechanical systems were centralized in mechanical floors, placed strategically throughout the tower to enhance vertical distribution efficiency for HVAC, electrical, and water services. A state-of-the-art building management system was integrated to optimize energy performance, aligning with sustainability goals such as LEED Platinum certification. Exterior cladding involved a prefabricated unitized curtain wall system made from high-performance glass and aluminum, ensuring thermal performance and acoustic insulation, while also accelerating installation timelines. The logistical orchestration of material deliveries, workforce scheduling, and vertical transport was critical to keeping the project on schedule. A just-in-time delivery approach minimized on-site storage needs, and hoists were positioned to optimize crew movement throughout the tower. Safety protocols were rigorously enforced, with daily toolbox talks and regular inspections conducted by site safety managers to ensure compliance with all local building codes and OSHA standards. The Gateway Program's Hudson River Tunnel project represents a monumental infrastructure undertaking aimed at revitalizing and expanding one of the most vital transportation corridors in the northeastern United States. This new tunnel system is designed to supplement and eventually replace the existing North River tunnels, which were constructed over a century ago and now suffer from significant age-related deterioration, exacerbated by saltwater intrusion and long-term corrosion following flooding events like Hurricane Sandy. The existing pair of single-track tunnels serves Amtrak and New Jersey Transit, handling over 200,000 passengers daily. However, their declining reliability poses a risk to the entire Northeast Corridor, prompting the need for a resilient, future-ready alternative. Construction of the new tunnel involves the boring of 2 single-track tubes beneath the Hudson River, running approximately 2.5 miles between New Jersey and Penn Station in Manhattan. The tunneling process utilizes tunnel boring machines, which are designed to handle the soft silt, clay, and varying geotechnical conditions beneath the riverbed. These TBMs will advance incrementally, supported by trailing systems that manage segmental lining installation, muck removal, and logistical support for ventilation and electrical systems. The tunnel lining consists of precast concrete segments sealed with gaskets to prevent water ingress and resist ground pressure. Before tunneling can begin, extensive site preparation is required, including the establishment of staging areas, slurry walls, and vertical access shafts on both riverbanks. These shafts will be used to lower components and remove excavated material. In areas of weak or waterlogged soils, ground freezing or jet grouting techniques are applied to stabilize the excavation zones and minimize settlement risks. The alignment must navigate beneath existing infrastructure, including utility corridors, building foundations, and transit lines, necessitating precise geospatial mapping and monitoring systems to track ground movement and ensure safe clearance. Inside the tunnels, systems installation includes high-capacity power supplies for ventilation fans, fire suppression systems, track infrastructure, overhead catenary for electric trains, and robust drainage channels to handle stormwater and seepage. The tunnels will also be equipped with advanced signaling and communication systems to integrate seamlessly with existing rail operations. Once operational, the new Hudson River Tunnel will allow for phased rehabilitation of the old tunnels without disrupting service. This project not only enhances capacity and reliability, but also ensures the long-term viability of high-speed and commuter rail service across the region, marking a critical investment in sustainable, resilient transportation infrastructure. The replacement of the Port Authority bus terminal in Midtown Manhattan represents a complex and transformative infrastructure project intended to modernize the busiest bus terminal in the Western Hemisphere. Originally opened in 1950 and expanded in the 1980s, the existing terminal has long surpassed its design capacity, accommodating over 200,000 passengers and more than 7,000 bus movements daily. Aging facilities, structural fatigue, and insufficient throughput have necessitated a comprehensive redevelopment effort that incorporates advanced engineering solutions and phased construction techniques to maintain ongoing operations. The replacement project involves constructing a new, state-of-the-art terminal with increased capacity, enhanced pedestrian flow, and modern amenities, while also integrating sustainable design features and improving surrounding urban connectivity. One of the most significant challenges lies in maintaining uninterrupted service during construction. To address this, a multi-phase plan has been developed. The first phase includes the erection of temporary bus loading and unloading facilities adjacent to or near the existing terminal footprint. These temporary structures are designed with modular steel framing and precast concrete slabs to allow for rapid assembly and disassembly. Once temporary facilities are operational, selective demolition of the old terminal begins. This demolition process is executed in controlled stages, employing heavy machinery such as high-reach excavators and hydraulic breakers, while implementing structural bracing to ensure the stability of adjacent buildings and infrastructure. Vibration and noise mitigation measures, including acoustic enclosures and real-time monitoring sensors, are deployed to minimize disruption to the densely populated surroundings. The foundation for the new terminal involves deep pile driving and the excavation of multiple basement levels to accommodate bus staging areas, mechanical rooms, and service corridors. Foundation work is coordinated with the Hudson Yard's rail yard infrastructure and existing subway tunnels, requiring precision excavation and protection of existing transit assets. Structural steel erection follows, with a composite steel and concrete framework designed to support high live loads associated with bus traffic and passenger occupancy. The new terminal incorporates high-efficiency HVAC systems, regenerative braking for vertical transport, daylight harvesting through skylights, and stormwater reuse systems. Bus operations are improved through a redesigned ramp system and expanded gates, optimizing ingress and egress while reducing idling times. Finally, integration with the existing subway and pedestrian pathways ensures seamless multimodal connections. Through a phased, engineering-intensive process, the Port Authority bus terminal replacement aims to deliver a 21st century transportation hub that meets current demands and accommodates future growth. The Fifth Avenue redesign in New York City represents a strategic urban infrastructure project focused on reimagining one of the city's most iconic corridors through a balance of engineering precision, traffic optimization, and pedestrian prioritization. The objective is to transform the stretch from Bryant Park to Central Park into a more accessible, multimodal, and resilient urban space without compromising the structural and operational needs of a high-capacity thoroughfare. This requires not just aesthetic improvements, but also deep civil engineering interventions and comprehensive utility coordination beneath the surface. The redesign begins with detailed site surveys, including topographical mapping, subsurface utility engineering, and geotechnical borings to determine the condition of existing pavement, vaults, and buried infrastructure. One of the first construction phases involves the mill and overlay or full-depth reconstruction of the roadway, depending on subgrade conditions. Drainage systems are upgraded using perforated pipes, additional catch basins, and bioretention elements to improve stormwater management and reduce surface runoff during peak rain events. To accommodate widened sidewalks and new pedestrian amenities, curb lines are realigned using new granite curbs and concrete base work. Subsurface utility relocation is a critical component of this realignment. Crews coordinate with utility providers to reroute electrical ducts, telecommunications conduit, and water mains, often working at night to minimize disruption. Con Edison vaults and manholes are either reinforced or relocated to support new sidewalk layouts and street furniture installations. The design incorporates dedicated bus lanes and protected bike lanes separated from vehicular traffic by precast concrete barriers or landscaped buffers. Pavement markings are applied using thermoplastic striping materials, and loop detectors or infrared sensors are embedded in the roadbed for traffic signal prioritization and adaptive control systems. Bus stops are redesigned with raised boarding platforms compliant with ADA standards, reinforced to support the weight of articulated buses. Lighting and streetscape elements are upgraded using energy-efficient LED fixtures mounted on architecturally styled poles with embedded conduit for future smart city sensors. Tree pits are re-engineered with structural soil cells and aeration systems to support healthy urban canopies. Modular pavers and tactile warning surfaces are installed to delineate pedestrian zones and ensure accessibility for all users. Through meticulous civil works, coordinated utility upgrades, and a phased construction approach that minimizes impact on businesses and residents, the Fifth Avenue redesign achieves a balance between heritage preservation and contemporary functionality, serving as a model for pedestrian-centric infrastructure renewal in a dense urban environment. The construction of the New York City Football Club Stadium represents a major engineering and logistical endeavor designed to deliver a dedicated, state-of-the-art soccer venue within the urban fabric of Queens, adjacent to the Willets Point redevelopment zone. The project involves transforming an underutilized industrial area with poor soil conditions, limited existing infrastructure, and significant contamination into a modern sports complex capable of accommodating over 25,000 spectators. Site preparation begins with extensive environmental remediation, as the area historically served as an auto salvage and industrial zone. Soil testing identifies the presence of hydrocarbons, heavy metals, and debris. Excavation contractors remove and replace several feet of contaminated fill with engineered clean soil, and ground improvement techniques such as dynamic compaction and aggregate piers are employed to achieve suitable load-bearing capacity for the stadium's foundation. The foundation system consists of a combination of deep concrete piles and pile caps supporting a reinforced concrete slab on grade. Because of high water tables in the area, dewatering wells and waterproofing membranes are essential during excavation and foundation installation. Drainage systems include underdrain networks and detention tanks to manage stormwater in compliance with municipal regulations and prevent localized flooding. The stadium's superstructure incorporates a hybrid steel and precast concrete frame, optimized for rapid assembly and long-span structural performance. The lower bowl is formed using cast-in-place concrete risers supported by grade beams, while upper tiers utilize prefabricated components lifted into place by high-capacity crawler cranes. The roof canopy, a critical feature for both aesthetics and acoustics, is constructed using cantilevered steel trusses and tensioned membrane panels that provide shade and amplify crowd noise. Mechanical, electrical, and plumbing systems are integrated through centralized utility corridors and mechanical penthouses, with provisions for HVAC zoning, fire protection, and emergency egress systems that meet stadium safety codes. A high-density Wi-Fi network and broadcast infrastructure are embedded into the structural framework to accommodate media and fan engagement technologies. Exterior cladding features a combination of metal panels, curtain wall glazing, and dynamic LED lighting elements. Pedestrian access is facilitated by wide concourses, ADA-compliant ramps, and public plazas that link the stadium with adjacent transit infrastructure. Throughout the project, a strict construction schedule and phasing plan are maintained to coordinate trades, manage supply logistics, and ensure timely delivery in alignment with league operations and community commitments. The development of 520 Fifth Avenue in Manhattan marks a significant vertical construction project blending commercial, residential, and retail functions within a slender, high-rise footprint. Situated in the heart of Midtown, the site demands meticulous engineering coordination due to its constrained dimensions, adjacency to active structures, and dense subterranean infrastructure, including subway lines and utility corridors. The tower is designed to rise over 800 feet, making it one of the more prominent additions to the Fifth Avenue skyline. Construction begins with site clearance and excavation, involving the demolition of previous low-rise buildings and removal of foundation remnants. Given the tight urban lot, perimeter slurry walls are constructed using hydromill trenching to form a watertight barrier during excavation. These slurry walls are tied back with rock anchors drilled into the Manhattan schist to resist lateral earth and hydrostatic pressures. A reinforced concrete mat foundation is then poured, with embedded column base plates to accommodate the building's steel superstructure. The tower's structure is a composite system of steel framing with concrete encased core walls, offering both vertical load-bearing capacity and lateral resistance against wind forces. High-strength steel columns and beams are fabricated off-site and delivered just in time for erection to minimize staging requirements. Tower cranes anchored to the core facilitate steel placement, while temporary hoists and material lifts ensure uninterrupted vertical transport for trades. Floor construction employs metal decking with concrete slabs, reinforced using welded wire mesh and shear studs for composite action. The central core, housing elevators, stairwells, and mechanical risers, is constructed using slip-form concrete techniques, allowing for accelerated vertical progress. Fireproofing and spray-applied thermal insulation are applied in phases as structural framing is completed on each floor. Mechanical, electrical, and plumbing systems are distributed vertically through the core, with horizontal branch routing coordinated through BIM modeling to avoid clashes. Air handling units, condenser water systems, and emergency generators are located on mechanical floors and roof levels, designed to comply with New York City energy and building codes. The exterior cladding consists of a high-performance curtain wall system integrating glass, aluminum mullions, and architectural metal panels. Installation follows the steel framing, with unitized panels hoisted and anchored from floor slabs. The building's base features retail space with double-height glazing and integrated canopies, while upper levels include luxury residences and amenity spaces with structural slab offsets and transfer girders to create spatial variety. 520 Fifth Avenue exemplifies complex high-rise engineering within tight constraints, showcasing integration of modern construction techniques and urban design sensibilities. Essex Crossing in New York City is a transformative, multi-phase development located on the Lower East Side, built over several city blocks of formerly underutilized land that had remained largely vacant since urban renewal efforts in the mid-20th century. The project comprises over 2 million square feet of mixed-use space, including residential units, commercial and office space, community facilities, and a variety of infrastructure upgrades. Construction has been phased to allow concurrent development of multiple parcels, each requiring tailored foundation, structural, and utility solutions due to varying site conditions and programmatic needs. Initial site preparation involved environmental remediation, demolition of existing structures, and relocation or protection of legacy utilities. Given the area's historical use and fill material, extensive soil testing and geotechnical analysis were conducted to determine suitable foundation strategies. For most parcels, deep pile foundations using drilled caissons or driven piles were installed to transfer loads to competent strata beneath the variable fill and soft clay layers. Excavation was performed using secant pile walls or soldier piles with lagging, supported by internal bracing systems where needed due to the proximity of adjacent properties and public sidewalks. The superstructures of Essex Crossing's buildings vary from concrete flat slab systems for residential towers to structural steel framing for larger commercial and retail floors, such as those housing the Market Line or cinema complexes. Floor plates are designed to accommodate multiple occupancies, with podium levels containing large open spans for retail, while upper levels incorporate repetitive structural grids for residential efficiency. Precast planks, cast-in-place slabs, and composite steel decking systems are selected based on load requirements and construction sequencing. A significant engineering feature is the integration of new infrastructure, such as upgraded stormwater detention systems, centralized mechanical plants, and utility corridors that serve multiple parcels. Mechanical, electrical, and plumbing systems are distributed via centralized shafts with floor-by-floor coordination for tenant-specific fit-outs. Roof levels are equipped with green roof assemblies, mechanical equipment screened by architectural enclosures, and solar arrays to meet sustainability targets. Public space enhancements, including plazas and widened sidewalks, required coordination with the Department of Transportation for curb realignments, utility vaults, and street lighting upgrades. Streetscape elements are constructed using reinforced concrete pavers, structural soil systems, and ADA-compliant grading. Essex Crossing exemplifies coordinated megablock urban redevelopment, combining deep foundation engineering, phased logistics, and mixed-use integration within a dense historic neighborhood. The Cornell Tech campus on Roosevelt Island in New York City represents a major academic and infrastructure development that transformed a previously underutilized hospital site into a state-of-the-art technology and research hub. The project required extensive site remediation, flood resilience planning, and high-performance building integration, given the island's constrained geography, proximity to the East River, and the need for long-term adaptability in a changing climate. The campus, spanning several phases, includes academic buildings, residential towers, open space, and energy-efficient utility systems. Site preparation involved the demolition of former hospital structures and the removal of contaminated soils and underground infrastructure. Flood protection strategies were incorporated early in the planning phase, including site elevation changes, reinforced perimeter drainage systems, and watertight construction zones to mitigate storm surge risk. Bulkhead improvements along the waterfront included new riprap revetments and engineered flood barriers integrated into landscape design features. The first academic structure, the Bloomberg Center, employed a structural steel frame with composite decking, engineered for flexible interior layouts. The building features an envelope of aluminum panels and triple-glazed curtain walls optimized for thermal performance. It operates as a net-zero energy building, relying on a geothermal exchange system, photovoltaic arrays, and a sophisticated building management system for energy regulation and data collection. The adjacent Tata Innovation Center features a hybrid steel and concrete structural system with wide-span trusses that enable large collaborative workspaces. The structure is clad in high-performance glass and metal curtain walls with solar shading devices and operable windows for passive ventilation. The building includes a double-height mechanical penthouse with green infrastructure and HVAC systems designed for tenant flexibility and future retrofits. A prominent vertical element is the house, a residential tower constructed using modular components. The modules were prefabricated off-site and craned into place onto a concrete core, significantly reducing on-site construction time and labor requirements. The building incorporates passive house standards, utilizing continuous insulation, triple-pane windows, and an airtight envelope to drastically reduce energy consumption. Subsurface utilities across the campus include a centralized energy plant, chilled water distribution, electrical duct banks, and stormwater management systems, all coordinated through building information modeling. Site hardscaping includes permeable pavers, bioswales, and resilient planting schemes to handle water runoff and reduce urban heat island effect. Manhattan West is a large-scale, mixed-use development in the Hudson Yards district of Manhattan, engineered over a complex site that includes active rail infrastructure operated by Amtrak and NJ Transit. The project encompasses several high-rise towers offering office, residential, and hotel spaces, along with extensive retail and public plazas. The engineering centerpiece of the development is the massive platform constructed above the rail yard, allowing for vertical expansion without disrupting the critical transit operations beneath. Platform construction required the installation of more than 300 caissons drilled between live tracks into bedrock, supporting a steel and concrete decking system. Crews utilized night and weekend windows to carry out this work, deploying customized drill rigs mounted on gantries spanning the tracks to avoid interfering with train schedules. Once caissons were installed, steel transfer girders and plate girders were placed across the yard, using large capacity crawler cranes and strand jacks, forming the framework of the platform. Precast concrete planks and cast-in-place topping slabs completed the surface, establishing a structurally sound and vibration-isolated base for the towers. The superstructures of the towers vary in composition. The tallest, One Manhattan West, utilizes a composite steel frame with a concrete core designed to accommodate high lateral loads due to the tower's slenderness and height exceeding 900 feet.